Section 8.2. Ciphertext only solution. It is also possible to solve multiplex ciphers when there are no known words. This is called a ciphertext only solution. I was the first person to find such a solution. Computer Methods for Decrypting Multiplex Ciphers, Cryptologia 2, April 1978, pages 152 to 160. In the original 1978 paper, I used bigram frequencies and worked up to trigrams. Computers today are much faster and have much more storage, so we can skip the bigram step. The method assumes that you have a table giving the probabilities for each possible trigram in English. You can compile such a table yourself, or just download a trigram table from the internet. Here is the gist of the method. Let us assume, as before, that Emily is using the M94 device with 25 cipher alphabets, and that we have intercepted a message of at least 3 blocks or 75 letters. All that we know about the message is that it is in English. For example, suppose we have intercepted. Start by trying all possible choices for the first 3 disks. There are 25 times 24 times 23 equals 13,800 such choices. For each choice, set the disks to the first 3 letters in each block of the ciphertext, namely CLP, ESI, and GAF. For each of these trigrams, look at the other 25 rows. These rows contain the possible plaintext trigrams corresponding to the ciphertext trigrams. Since there are 25 choices for each of the 3 rows, the total number of possibilities is 13,800 times 25 to the power 3 equals 215,625,000. This can be easily handled by a desktop computer or even a notebook computer. For each combination of 3 disks and 3 rows, the probability of that combination is the product of the probabilities for the 3 plaintext trigrams. Equivalently, the logarithm of the probability is the sum of the logarithms of the 3 trigram probabilities. The idea is to keep only the most likely combinations and discard the rest. For example, you could keep only the top 1%, or you could keep a fixed number of good combinations, perhaps the 1 million best. Let's assume that you chose to keep the top 2 million. One way to do that is to generate all 215,625,000 combinations, then sort them on the probability and throw out the bottom 99%. That would take a lot of storage. There are better ways to do this. Start by allocating a table that is 10% to 25% bigger than the number of combinations you want. Let's say 2,500,000 combinations. Begin generating the combinations and put them in the table. When the table gets full, it needs to be trimmed by about 20%. This could be done by sorting the table and deleting the bottom 20%. That is, you sort by descending probability and then just set the number of table entries to 2 million. Sorting out 2,500,000 items is a lot faster than sorting 215,625,000 items. But there are far faster ways. Select 10 items from the table at random. If you don't know how to choose randomly, choose the items 1/11, 2/11 to 10/11 of the way through. Sort these 10 items from least probable to most probable. Call these sorted items A, B, C, D, E, F, G, H, I, J. Let P be the probability of item B. Delete every item in the table whose probability is less than P. Continue generating combinations, but do not add any item to the table whose probability is P or less. Each time the table fills up, repeat the process of sampling, sorting the samples and resetting the cutoff probability P. At the end of all this, you will have about 2 million combinations of 3 disks and 3 rows. The next step is to extend this to 4 disks. Try all 22 possible choices for the fourth disk. This will give you about 44 million combinations. Now look at the trigrams formed by disks 2, 3 and 4. For each combination, multiply the probability for the trigram on disks 1, 2, 3 by the probability of the trigram on disks 2, 3, 4 to get an approximate probability for the tetragram on all 4 disks. Multiply the probabilities for the plaintext tetragrams corresponding to the 3 ciphertext tetragrams CLPO, ESIW and GAFO. This will give you the probabilities for the 44 million combinations of 4 disks and 3 rows. Again, you can keep the best 1% to give you 440,000 sets of tetragrams. Use the same method as you used for the trigrams. Continue this way to get the pentagrams, hexagrams, heptagrams, and so forth. Each time you add a disk, you can keep fewer combinations than the time before. When you get down below 100, you can just pick out the correct combination by sight and complete the solution by hand. One problem that may cause this procedure to fail is this. Even in normal text, a trigram may appear that has a probability of 0 in your trigram table. If Emily is using nulls, this may occur fairly often. This could cause the legitimate plaintext to get rejected. One solution is to jigger the trigram probabilities so that a 0 probability never occurs. Let's write P of x for the probability of a string x. If the probability of a trigram, say xyz, is 0, you can use the greater of P of x times P of y and z, and P of x and y times P of z. I suggest dividing this by 3, say, because xyz never occurred in your trigram count. If the probability of xyz is still 0, then use the individual letters. For example, set P of x, y and z to P of x times P of y times P of z over 10. A different solution is not to multiply the probabilities, but to use some other function to combine them. For example, you could add the sum of the squares of the probabilities. This will strongly reward common trigrams, while largely ignoring rare trigrams. If all of this fails, then simply try the procedure again from a different starting point in the ciphertext. For example, start at the 5th disk.